With the coming of the James Webb Space Telescope, JWST, the most modern telescope ever built, we presently have the means to explore the possibility of extraterrestrial life as we direct our attention to the closest star system, Proxima Centauri, which is just 4 light-years away. Researchers have made an astonishing discovery among the planets circling this distant star. Proxima B displays bizarre peculiarities and artificial lights that defy explanation. These astonishing findings have perplexed mainstream scientists and sparked hypotheses about the possible presence of intelligent life. Join us as we investigate the pivotal discoveries mentioned by JWST, objective evidence of city lights that challenge our understanding of the universe. American astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI project in 1984. This charitable endeavor aims to detect spaceborne radio transmissions using the novel capabilities of the Allen Telescope Array located in the Californian Fountain Mountains. Despite 30 years of tireless observation, no definitive proof of extraterrestrial communication has emerged. Following the launch of JWST, the mission to examine a range of distances and unseen planets circling distant stars has gained momentum. The largest telescope in the world, which is drifting approximately 1 million miles from Earth and equipped with incredibly sensitive detectors, will be used. Years ago, there were no known planets outside those in our solar system. However, since then, more than 4,000 exoplanets have been discovered orbiting different stars. According to NASA, the universe may contain trillions of exoplanets. The earliest indications of life beyond our solar system might be observed in extraterrestrial vegetation. While visiting Jupiter, the Galileo spacecraft turned its instruments back toward Earth and found a clear indicator of vegetation when sunlight crossed a planet's star. JWST might be able to identify it as it enters the planet's atmosphere. The instrument detected the vegetation red edge, which is a combination of red and infrared light reflected by plants. For example, a planet like Earth, covered in a forest, should have a strong and easily detectable red edge. JWST will measure the red edge of distant Earth-like planets in the habitable zone around stars, which could be critical indicators of life in the exoplanet's atmosphere. Spectroscopy would next be utilized to identify the missing frequencies. Molecules and particles in the atmosphere absorb specific frequencies, resulting in a distinct signature that JWST can identify. This method can be used to discover the atmosphere's composition and the possibility of life. It is conceivable that life could exist on planets the size of Earth that have atmospheres comparable to ours, with a mix of oxygen, nitrogen, and carbon dioxide. One could potentially identify artificial life by searching for components that are not commonly present, such as chlorofluorocarbons, CFCs. Even natural life, such as extremophile species, can sometimes appear alien. These species are a group of microbes that can survive in conditions where other living things would perish. CFCs produced for use in refrigeration and cleaning products would likely be recognizable to extraterrestrials monitoring Earth's atmosphere from a distance. If JWST detects CFCs in planetary atmospheres, that would sound a clear signal of advanced life. Some organisms can survive in strong acidity, with pH values below 3, while others can endure temperatures as low as 4 degrees Fahrenheit. Certain organisms can withstand heat up to 250 degrees Fahrenheit, and some can be found on Earth where we wouldn't expect to find any life at all. Could be a wise idea to start with those first, as planets like Earth are more likely to harbor life than planets with extreme temperatures or acidic conditions. Ideal candidates could orbit a stable star at temperatures that allow liquid water to exist on their surfaces. Our Sun is classified as a yellow G-type star, which is less frequent and typically has a shorter lifespan in our universe. Red dwarf stars are more common than other stars and have lower temperatures and brightness than the Sun. Thanks to their longer life expectancies of about 40 billion years, there is more opportunity for the evolution of life and development of complex life forms on these planets, increasing the likelihood of studying planets orbiting these stars. The initial mission of JWST will focus on a single planetary system that has 7 rocky planets the size of Earth orbiting a quiet red dwarf star. It is possible that the surfaces of 3 of the rocky planets in the so-called habitable zone contain liquid water based on the planet's orbits. A single star emits light indistinguishable from our Sun's. despite having a significantly smaller and cooler mass. Proxima Centauri, a red dwarf star 425 light-years from the Sun, is an excellent place for humanity to search for city lights beyond the solar system. Proxima Centauri is our closest star and is multiple times fainter than the Sun, meaning that a planet must be 20 times closer to it than Earth is to the Sun for it to support life based on liquid water. A planet with multiple times the mass was discovered by researchers in August 2016 in this habitable zone, which resembles a Goldilocks zone with light intensity just right to melt water. Given that Proxima B orbits its red dwarf star, Proxima Centauri, at a distance of just 46 million miles, its nature makes it a potential airless, dormant body. Proxima B is subjected to strong winds that have the ability to obliterate its atmosphere. However, it also receives enough sunlight to maintain temperatures and liquid water comparable to those on Earth. Due to its close proximity to Proxima, it is believed to be tidally locked, always showing the same side to the star as the Moon does to Earth. Proxima Centauri, which is only 18% of the mass of the Sun, shines much dimmer than one would expect for a planet that is only 5% of the distance between Earth and the Sun. This means it is likely to be a red-hot planet, since only 65% of Earth's energy comes from the Sun. Liquid water could easily exist on Proxima B as long as the planet has an atmosphere to warm it. However, Proxima B isn't particularly hospitable to life. It is likely tidally locked, meaning that it always faces the same direction toward the star, resulting in permanent day and night sides with significant temperature changes. Due to its proximity to Proxima Centauri, the planet also receives 100 times as much high-energy radiation as Earth, including X-rays and ultraviolet light. Proxima B is also bombarded with high-energy particles during star eruptions, and unless it has a magnetic field structure like Earth's, it isn't particularly hospitable. Nonetheless, there are certain practical conditions that could make it an intriguing world. Tragically, models suggest that the atmosphere of tidally locked planets might be susceptible to rapid breakdown due to the freezing out of volatile gases on the night side. A planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we don't have much knowledge of Proxima's volcanic activity or magnetic field strength, we cannot determine whether the planet has an atmosphere yet. Since an atmosphere implies the presence of seas, and the two taken together imply the presence of life, we are eager to know whether Proxima B has an advanced civilization. It could have solar panels covering the day side to generate power to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine whether it transits its star as seen from Earth. These transits would allow scientists to determine the planet's size and mass, which would then enable them to ascertain its density. Knowing that would confirm the planet's rocky composition and provide information on the materials used to make those rocks. During a transit, light passing through the planet's atmosphere might reveal information about it. However, only 15% of the time would the orbit be in the proper alignment for scientists to observe a transit, and the tendency of stars to flare further complicates matters. The star is unstable, according to Columbia University astronomer David Tipping, as its intensity causes rocky planets like Proxima B to absorb sunlight and emit infrared light. However, rocky planets also produce a different kind of infrared radiation from stars. Moreover, JWST was built explicitly to focus on infrared light, which is crucial for determining Proxima B's atmosphere through its infrared heat signature. Additionally, since water is strongly attracted to this part of the spectrum, JWST will be able to detect city lights on Proxima B's night side, even if they are as faint as those that our civilization uses on Earth's night side. Due to the specific spectral edges as Proxima turns around its star, we could detect artificial lighting as long as it was restricted to a frequency band that is many times smaller than the star's. Proxima B's day side is heavily covered with solar panels 24/7, which are indistinguishable with cool evening lows following daytime highs. The temperature difference between the day and night sides of Proxima B will depend on whether the planet is made entirely of exposed rock, as both the ocean and atmosphere conduct heat. In other words, if Proxima B lacks an atmosphere, the day and night sides will differ more in temperature. In fact, since the day side of Proxima Centauri emits all the energy it receives from the planet as a black body, we can determine the exact amount of black body radiation that should be present on the night side. On the other hand, the night side will appear as a frozen version of hell. If Proxima B has an atmosphere, it will only take JWST 10 to 20 Earth days to measure the radiation from its two faces after it has successfully completed its orbit around the star. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, the next step will be to examine its composition for any gases present. To do this, however, we must successfully capture starlight as it bounces off or passes through the planet's atmosphere, which is a challenging task. JWST can closely examine a few of the nearest potentially habitable worlds, as it was not designed to search for extraterrestrial life. Moreover, it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. Oxygen, water vapor, and methane, in particular, could indicate the presence of habitable conditions, if not actual living things. Regardless of whether some combinations of these gases might suggest life, JWST cannot detect the presence of unbonded oxygen, which is the best indicator of life. Ozone might be among the substances that JWST is capable of identifying. Until those telescopes are operational, the Very Large Telescope is planned to begin activity in the 2020s, making it one of the ground-based observatories that will be able to conduct a thorough atmospheric investigation. In 10 years, JWST may provide data that will be relevant to us. Meanwhile, even more powerful space telescopes could employ advanced techniques to block the blinding brilliance of the host star and reveal the planet's reflected starlight. Future space telescopes, using large external umbrella-shaped shields or small internal covers, could capture the planet's reflected starlight. It is fundamentally easier to focus on light glimmering off a planet. Unfortunately, non-biological processes can also produce most of the gases emitted by terrestrial life. Both cows and volcanoes produce the gas methane, and the most common way of searching for extraterrestrial life is sunlight, which uses photosynthesis to convert water molecules into oxygen and hydrogen. Therefore, some false positives for alien life are inevitable. To determine if a planet of interest's geography or atmospheric cycles could resemble a biosignature and help rule out false positives, astronomers need to have a strong grasp of the world. The next round of exoplanet studies could yield the convincing evidence needed to demonstrate that life exists. The initial data from JWST gives us a glimpse into the significant advancements that are on the horizon. One of science's most important questions is whether there is life elsewhere in the universe or whether we are the only species on a lonely planet in deep space. In any case, major philosophical and psychological shifts among people will likely be required for the inevitable revelation. Humans have entertained fantastical ideas about the possibility of life on distant celestial bodies. These thoughts have been fueled by both scientific exploration and science fiction. Yet it was only after the arrival of groundbreaking technological wonders like the James Webb Space Telescope that the enticing possibilities of life in the universe became more tangible. JWST stands as a beacon of human ingenuity, representing the pinnacle of observational capability. With its unrivaled capacities, it promises to revolutionize our understanding of the universe, allowing us to peer farther into the cosmos than ever before. Equipped with this technological marvel, researchers set their sights on the nearest star system to our own, Proxima Centauri, located a mere 4 light-years away. This enormous neighbor entices with the allure of discovery. Within the Proxima Centauri system lies Proxima B, a planet shrouded in mystery and intrigue. It is here that researchers have identified strange anomalies and artificial lights, casting uncertainty upon the long-held beliefs of a barren expanse. These cryptic findings have baffled even the brightest minds within the academic community, igniting intense speculation about their origins and implications. Could these artificial lights be harbingers of intelligent life lurking amid the vast expanse? The very thought sends shockwaves through the scientific establishment, challenging long-held assumptions about humanity's place in the universe. As experts grapple with this profound question, JWST stands poised to unravel the mysteries of Proxima B, offering glimpses into the unknown and potentially reshaping our understanding of life's cosmic prevalence. Yet the search for extraterrestrial intelligence extends far beyond the confines of our own cosmic backyard. Since time immemorial, humans have looked skyward, pondering the presence of companions among the stars. This quest for cosmic kinship found renewed vigor with the inception of the search for extraterrestrial intelligence. SETI project, led by visionary cosmologists Jill Tarter and Tom Pearson in 1984. Armed with a variety of cutting-edge technologies and employing radio telescopes to scan the vastness of space in search of elusive signals, SETI aims to probe the universe for signs of intelligent life.